So what we're actually going to be looking at is the physics behind car crashes. So to understand the physics behind car crashes, the first thing we need to understand is momentum. Now, momentum is a vector, so like force, velocity, or acceleration, it's got a magnitude and also a direction. So momentum can be calculated as the product of the mass of the object and the velocity of the object. So momentum is generally given the symbol a lowercase p. So our formula for momentum is P is equal to mv. The units for momentum are kilogram meters per second or Newton seconds. So the definition of momentum is in alignment with our everyday usage of the word momentum. We tend to say that heavy objects such as trucks have a lot of momentum, and then lighter objects like a toy car have a lot less momentum. So momentum is just the product of the mass and the velocity. Let's do an example now where we will calculate the momentum of an object.
So this question says, a truck has a mass of 7,000 kilograms and a car has a mass of 1,200 kilograms. Both are travelling northward at 110 kilometers per hour. Calculate their momentum. So in order to calculate their momentum, we're going to need to use the formula that the momentum is equal to mass times the velocity. So first of all, we'll need to convert this velocity into the velocity in meters per second. So the velocity is equal to 110 kilometers per hour, which is equal to 110 times 1,000 meters per hour. And then to convert it into seconds, we divide by 60 times 60, and that gives us 30.56 meters per second. So in order to calculate the momentum of the truck, we have that the momentum of the truck is equal to the mass of the truck, which is 7,000, times 30.56. So solving that on the calculator, we get 213,889 Newton seconds. Now we should probably give this to two significant figures. It's hard to tell, but this data could be to 2 or 3 significant figures. So let's give it to 2 significant figures. So that's 210,000 Newton seconds to 2 significant figures. And then momentum is a vector, so we should also give a direction. And so since the velocity was northwards, this momentum is also northwards. So northwards. And now we need to do it for the car. So the momentum for the car is equal to the mass of the car, which is 1,200, times the velocity of the car, which is 30.56 meters per second. So this is equal to 36,672 Newton seconds. So to two significant figures, this is equal to 37,000 Newton seconds, and that's to two significant figures. And now we also need to include the direction. So the direction on this momentum is northwards.
Now, in order to change the momentum of an object, we need to apply a force to the object. So we can actually use Newton's second law to derive the relationship between the force applied on the object and its change in momentum.
So to use Newton's second law to derive the relationship between the change in velocity and the force, we have that the acceleration is equal to the net force over the mass. That's just Newton's second law, which tells us that the net force acting on an object is equal to the mass times the acceleration of the object. Now we defined acceleration as the rate of change of the velocity. So this is just equal to the change in the velocity over the time. These little squiggly lines underneath these letters represent that this quantity is a vector. So this velocity is a vectorial quantity. It's got a direction as well as a magnitude. And so what we can do is substitute this expression for the acceleration into this formula up here. So that tells us that the net force is equal to the mass times the change in the velocity over the time. And now the mass times the change in velocity. Now we can write that change in velocity as the final velocity minus the initial velocity. That's just what the change in velocity means. And so we've got mvf minus mvi on t. And this is just the final momentum and this is the initial momentum. So this is equal to the final momentum minus the initial momentum over time. And so the final minus the initial, that's the change in the momentum over the time. And these momentums and velocities are all vectors and so should all have the squiggly line underneath them. So we've got that our net force is equal to the change in momentum over the time. So the total force acting is equal to the change in momentum over time. So we can also write this as the force times the time is equal to the change in the momentum, which is just equal to the mass times the final velocity minus the initial velocity.